We will now talk about duals of LP spaces. We have already done some of these computations earlier. So let us look at LNP, which I recall is Rn with the norm P. Okay, and so LNP star is LNP star for 1 less than or equal to P less than or equal to infinity. All these spaces being finite dimensional are reflexive, and therefore this holds for the entire range of values of P, where P star equal to infinity if P equals 1 and vice versa, and if 1 is less than P is less than infinity, then you have 1 by P plus 1 by P star equal to 1. So in particular, if P equals 2, this implies P star is also equal to 2. Okay, and then we have also computed LP star, and this is equal to L of P star. This is true for 1 less than or equal to P strictly less than infinity. And we have seen that L infinity star does not come from L1, it is something bigger. Okay, so these are the duals. So now we will study for the LP spaces given a measure space. So before that, one preliminary result. So in the case of L2 or L22, if you remember, right? So we proved the parallelogram law. So namely, norm of x plus y by 2 whole square plus norm of x minus y by 2 whole square is equal to 1/2 of norm x square 2 plus norm y square. So this was the parallelogram law, the Apollonius theorem in plane geometry, which can be generalized also to, in general, to Ln2, L2, etc. All these spaces have this identity valid. Okay, so now we are going to generalize this to LP spaces. It is available, such inequality, we won't get an equality, we will get an inequality, and it's available for all values of P in the range 1 to infinity, but 1 to 2 is difficult, so we will prove the easier portion of it. Okay, so proposition. This is called Clarkson's inequality. So let X S mu be a measure space. Let 2 less than or equal to P less than infinity. So if Fg belong to LP of mu, then you have norm of F plus G by 2 in LP to the power P plus norm of F minus G by 2 in LP whole to the power of P is less than or equal to 1/2 of norm F P to the P plus norm GP to the P. Okay, so this is the Clarkson's inequality, which generalizes the parallelogram law which we wrote earlier. So proof. So consider the function phi of x equals x squared plus 1 to the P by 2 minus x power P minus 1 for x greater or equal to 0. So then it is easy to see that phi 0 equals 0, and if you do the computation, phi dashed x will be positive for x positive, and this is because P is greater than or equal to 2. So that is the reason why we need this range of values of p. So you have this relationship, so it's just a straightforward computation of the derivative. So phi is an increasing function, starts at 0, and therefore you have, for x greater or equal to 0, you have that x squared plus 1 to the p by 2 is greater than or equal to x power p plus 1. And so if alpha beta are positive numbers, so then you have that alpha square plus beta square to the power of p by 2 is greater than or equal to alpha power p plus beta power p. All you have to do is to take x equals alpha by beta or beta by alpha as you wish. Okay. The other thing which we want to, so this is one. The second thing which we want is the function t going to t to the p by 2 is convex for t greater than or equal to 0. So all you need to do again is to take the second derivative of this function, and then because p is bigger than 2, you will get the second derivative is positive, non-negative, and therefore you have the convexity. Okay, so using these two results, we will now do the following. So norm of, so x in x, so fx plus gx by 2 power p plus mod fx minus gx by 2 power p. So this is alpha power p plus beta power p. So that is less than or equal to alpha square plus beta square to the p by 2. So that is mod fx plus gx by 2 whole square plus mod fx minus gx by 2 whole square to the power of p by 2. Now if you expand this thing, you will get f square 2 times divided by 4, that will be f square 1/2 of f square, g square 1/2 of g square, and then you will, the cross terms will cancel. So you will get that this is equal to mod fx square plus gx square by 2 to the power of p by 2. So now you use the convexity of the function t power p by 2. So this is the value at the midpoint, and therefore that is less than or equal to the average of the values at the endpoints. So this you have 1/2 of f square evaluate power p by 2, that will give you mod fx power p plus mod gx power p. So using, so here we used the convexity, and here you used 1. 1 is this relationship here. Okay, we used 1. Okay, by 1, and so here we use the convexity, and therefore, okay, so now you just integrate over x with respect to mu, and that will give you precisely whatever you want. Okay, so this is the proof of Clarkson's inequality. So corollary, so excess mu is a measure space, and then 2 less than or equal to p less than infinity, then Lp mu is reflexive. Okay, so we are going to prove it. So proof. So if you have norm Fp less than or equal to 1, norm Gp less than or equal to 1, and norm of F minus G P is bigger than epsilon, okay, then what you get from Clarkson's inequality is that norm f minus g by 2 p whole power p is less than or equal to 1/2 of norm fp plus norm gp. So that's each less than or equal to 1. So 1 plus 1, 2 divided by 2 is just 1. Sorry, f plus g by 2. So that is less than 1. And then you have minus norm f minus g is greater than epsilon. So you get, so this is greater than epsilon by 2. Power p. Okay, so you can write this as 1 minus delta whole power p, where you can compute what should be delta in view of this. You can write this like this, and therefore you get that norm f plus g by 2 p is less than 1 minus delta. So there exists delta such that for every epsilon positive, and therefore Lp mu is uniformly convex for 2 less than or equal to p less than infinity, implies reflexive. We have proved this theorem. Uniformly convex implies reflexive. Okay. So now we can prove our main theorem. So this is the Riesz representation theorem. So there is a whole family of theorems with the same name. So, and they are all about computation of duals of some function space or the other, the LP spaces, continuous functions, various things. So these are all attributed mainly to Riesz, who is a pioneer in this area of computing duals, and also representation. So the abstract linear functional is given a concrete representation in terms of known objects. Okay, so that is why it is called the Riesz representation theorem. So there's a whole family of such theorems. This is just one of them. Okay, so let x s mu be a measure space. Okay, and let 1 less than p less than infinity. Let p star be the conjugate exponent. Then Lp mu star, the dual, is isometrically isomorphic to Lp star mu. In particular, the spaces Lp mu 1 less than p less than infinity are all reflexive. Okay, proof. Okay, step 1. So let G belong to Lp star mu, and you define, as we have done earlier in the case of sequence spaces, Tg from Lp mu to R. So Tg acting on any f equals integral over x fg d mu, and this is for all f in Lp mu. Therefore, mod Tgf is less than or equal to integral over x mod fg d mu. F is in Lp, G is in Lp star, so by the Helder inequality, this is less than or equal to norm Fp norm G P star. So this is Helder, and therefore Tg belongs to Lp mu star, and norm Tg is less than or equal to norm G P star. So now you consider consider the function f of x to be defined in the following way. This is mod gx to the p star minus 2 gx if gx is not 0, and 0 if gx equals 0. See, if p star is less than 2, then p star minus 2 is negative, so gx will go to the denominator, so you will have trouble if you have gx equal to 0. So we avoid that, and then we put it as 0 if gx equal to 0. So essentially it is you can still say it is this, only gx to p star minus 2 is not defined if gx equal to 0. Okay. So then what is mod f to the p? Mod f to the p, if you take mod f, you get mod g to the p star minus 1 whole power p. P star p minus p is nothing but p star, so this is mod g to the p star. Okay. So this implies, and this is g, this is integrable because g is an LP star, and therefore f is p integrable. That is, f belongs to LP. Okay. And what is Tg of f? So I can apply f to this. So Tg of f, if you recall, is fg d mu. So you have to multiply f by g, so you get g square and p square minus 2, so you will get integral mod g to the p star over x d mu. Okay, so this is nothing but norm g p star to the power of p star. And what is norm fp? Norm fp power p is nothing but integral of f power p, so that is nothing but norm g integral mod g p star power p, and that's equal to norm g, sorry, that's right, norm fp, sorry, yeah, that's, it's just integral of this is norm g p star power p star, and therefore norm fp is norm g p star to the power of p star minus p by p. Okay, so if you substitute mod tgf by norm fp, you will get exactly norm g p star into 1 minus 1 by p, which is just 1, and so this will give you norm g p star. So this supremum of all this is norm Tg, and that is less than or equal to norm g p star, because we know norm Tg is less than or equal to norm g p star, but we have actually found an f for which it is actually attained, so this implies that norm Tg equals norm g p star. Okay, so you have that g going to Tg is an isometry from L p star mu into Lp mu star. So the image is a closed subspace of this. Okay, our aim is to show in fact the image is the whole thing. Okay, so step 2. So Lp reflexive for 1 less than p less than infinity. Okay. So if p is greater than or equal to 2, then you have that Lp mu is uniformly convex and therefore reflexive. So this is already done in the corollary. Okay, so we now look at okay, so now Lp mu, so this implies Lp mu star is reflexive implies any closed subspace is reflexive, implies P star mu is reflexive since it is isometrically isomorphic to a closed subspace of Lp mu star. Okay, so this is closed. But if P is P star, P is greater than or equal to 2, we have P star is less than or equal to 2. Okay, therefore, and every 1 less than P star less than P less than 2 is the conjugate exponent of some P greater than or equal to 2. Therefore, all spaces Lp mu 1 less than P less than 2 are also reflexive. Okay, so this way we have proved the reflexivity of all the functions. Now step 3. So now we will show that G to Tg is onto. Okay, so we have shown that it is isometric to a closed subspace, so we need to show that it is the whole space. So we will show image is dense in Lp mu star. Okay, so how do you show that? By the Hahn-Banach theorem. So if not, so or we just, you don't need to do the contrary. So let phi belong to Lp mu double star vanish on this image. So to show phi is identically 0. But Lp mu is reflexive. So this implies that there exists a f in Lp mu such that for all G in Lp mu star, Lp star mu, we have that for all G in Lp, we have that integral over x fg d mu equal to 0. Okay, because it vanishes on the image means Tg of f is 0, that is integral, that is Tg of f equal to 0. This is nothing but phi of Tg, and for all G in Lp star. This is the meaning of the statement here. So now again we will do the same trick. So now we define that take G equal to G of x equal to mod f to the p minus 2f of x mod of fx to the p minus 2 f of x if f of x is not 0, and 0 if f of x is 0. Once again for the same reason, like this, and then you can show, we can check as before. G is now in Lp star mu. Okay, and then if you now substitute this, so this so now we can use this for G in this relationship. So, and therefore you will get integral mod f to the p minus 2 f into f, so that will give you mod f to the p d mu of x equal to 0. This will imply that f is 0 in LP mu, and that implies that phi is 0. And therefore you have that the image is dense, but the image is already closed, so the image is equal to its closure, which is equal to LP mu whole star, and therefore so this implies that LP star mu image of LP star mu is nothing but LP mu star, and therefore it's isomorphism, and that completely proves the Riesz representation theorem in this case. Okay, so earlier, remark, we have seen that L1 star equals L infinity, but L infinity star is not L1 and so on. We have also seen that Ln infinity is Ln1 star, and Ln1 equal to Ln infinity star. Okay, these we either it's exercises or we have seen it. Okay, so now we have not studied anything about p equals 1 or infinity in this theorem. We have only looked at 1 less than p less than infinity. But if you look at if you want to show that L1 mu star equals L infinity mu, this can also be done. Now this involves very complicated long measure theoretic arguments. In fact, it's a package deal. This is proved, and simultaneously LP mu star is LP star mu is also proved. Okay, so the whole thing is proved, but it is fairly long proof and involves measure theoretic arguments, whereas here using functional analytic arguments we have very easily proved using reflexivity concepts about 1 for the case 1 less than p less than infinity. So this has been not been done, but on the other hand we will prove this result. So we will prove this in the case of L1 of omega. So we will show that L1 of omega dual is L infinity of omega. So I recall the definition of this. So we take omega in Rn and equipped with the Lebesgue measure. Okay, so that is the space L1 of omega. Okay, so in that case we will show that this is indeed true.